Imagine blasting off Earth at 28,000 kilometers per hour, floating in zero gravity and orbiting our planet without falling back down. Sounds like science fiction, right? Well, it's pure physics. And today, we're breaking down the forces, laws, and mechanics that make space travel possible. Let's start with the obvious. Getting off Earth is tough. Why? Gravity. Our planet pulls everything toward its center with a force so strong that to escape it, you need to hit what's called escape velocity, about 11.2 kilometers per second. That's 33 times the speed of sound. It's like throwing a ball. If you toss it gently, it falls right back. Throw it harder, it goes farther. But unless you throw it at escape velocity, Earth's gravity will always win. To really understand space travel, we need Newton. His 3 laws of motion are the backbone of rocket science. First law, inertia. Objects in motion stay in motion unless acted upon by another force. That's why astronauts keep floating in space. No air resistance, no friction. Second law, F equals ma. This one's huge. Force equals mass times acceleration. The bigger the rocket, the more thrust you need. That's why we pack rockets with giant fuel tanks. Third law, action and reaction. For every action, there's an equal and opposite reaction. A rocket pushes exhaust gases downward, and in return, the rocket shoots upward. Simple, but powerful. Here is the fun fact for you. NASA's Saturn V rocket produced 34 million newtons of thrust, enough to launch a skyscraper into orbit. Here's a mind-bender. Astronauts in the ISS aren't actually weightless, they're falling. The station is constantly falling toward Earth, but because it's moving forward so fast, about 28,000 kilometers per hour, it keeps missing Earth. That's an orbit. Picture standing on a giant mountain. If you throw a ball, it falls. Throw harder, it goes farther. Throw fast enough, and it keeps falling around Earth forever. That's orbit. Fun fact, satellites in low Earth orbit circle our planet once every 90 minutes. That means astronauts see 16 sunrises and sunsets every single day. Leaving Earth orbit takes even more careful planning. To reach the Moon, Mars, or beyond, spacecraft use something called transfer orbits. The most efficient is the Hohmann transfer, a curved path that uses the least fuel. Think of it like merging onto a highway. You can't just drive straight across. You follow a curve that smoothly matches speeds. Spacecraft do the same thing with planets. Fun fact, the Apollo missions reached the Moon in just 3 days. But Mars, that's a 7-month road trip at tens of thousands of kilometers per hour. Today, rockets are reusable thanks to SpaceX. Tomorrow, we may see nuclear propulsion, solar sails, or even ion drives, engines that trade brute force for efficiency, accelerating spacecraft to unimaginable speeds over time. Some scientists even dream of warp drives, inspired by Einstein's relativity, bending space itself to travel faster than light. It sounds like Star Trek, but the math isn't completely forbidden. So, the physics of space travel boils down to 3 things. Newton's laws, the foundation of rocket thrust. Orbital mechanics, the art of falling around planets. And human ingenuity, turning equations into exploration. The next time you see a rocket launch, remember, it's not just fire and smoke. It's centuries of physics, working in harmony with human ambition. If you enjoyed this breakdown of space travel physics, hit subscribe, drop a comment on what topic we should explore next, and share this video with a fellow space geek. Until next time, keep looking up.